belonging to mechanical branch. He has worked as a leading member in the mega project from Government of India, LIGO, Laser Interferometer Gravitational Wave Observatory. He has very wide experience of almost 22 years in designing, fabricating, installing and commissioning of various large systems like vacuum, cryogenic, structural systems. He has worked in the different areas like structural, thermal, CFD, materials, etc. He has many research publications in well-known reputed journals. He is the reviewer of many reputed journals. He has done his diploma, undergraduation, post-graduation and PhD in mechanical engineering. So that is the thorough journey of mechanical engineering. He is mentoring many projects related to thermal engineering. He has done many certificate courses from IITs. He is continuously delivering expert lectures in LD College of Engineering, Nirma University, Pandit Deendayal Upadhyay University, Delhi Technological University, Indus University. He is Board of Study, BOS member of GTU, Indus University, LDIP University. He is gold medalist. He has been awarded from the different Indian institutes and foreign bodies. He received the award as a part of LEGO team. 2016 Gerber Cosmology Prize provided to him by US government and 2017 Royal Astronomical Society Group Achievement awarded by the United Kingdom government. Special breakthrough prize he obtained in the fundamental physics by the US. It is at a part of Nobel Prize in 2017. So that is one of the most award to be get by any Indian continent person in the physics in the current days. Apart from technical, he is practicing, applying, regularly delivering lectures on the Bhagavad Gita too, spiritually at different platforms. He is a very good motivator. His personal life is very simple and dedicated to the society. Many programs have been currently running by him for the benefit of the society, poor and people who have economical background is poor. So it is our proud that we have received such time for to talk us on this topic today. So I welcome sir for to provide his valuable guidance and time in education of STP participants. Welcome sir.
Thank you very much, Dr. Jani, for giving the introduction. And it is my privilege that Dr. Shah and you have approached so that I can share some experience. But I am very sorry that I am late today due to some urgent meeting. now, now I am going to share. Are you able to see?
Yes, Gupta sir, your voice is very clear and PPT is available on our screen, sir.
Okay, okay. Thank you, Jani sir. After a long time, due to this program, we were able to talk each other, and he was the teacher during my MTech. Dr. Jani was so many
Thank
Dr.
you.
Shah and other things. So they have given the topic of use of cryogenic technology for air separation, and as I am working in the Institute for Plasma Research, uh, many people may or may not know. I don't know the things. So I will just give you a small brief introduction of our institute initially. and here we are using this cryogenics and this. Then I will go to the topic. So this institute is emerged in 1986 from PRL, which is also in the Ahmedabad. The objective was to do the research in nuclear fusion, basic and industrial applications with plasma. And the device here we are making the plasma is called as the tokamak. So in 1989, we have made the India's first indigenous tokamak reactor, and it became operational in 1989. And the name was given as the Aditya. Then it was the pulse device. Then we have started to work in the steady state condition. But the steady state condition, we need the superconducting magnets. So the next in 1994, we have made the one tokamak called the SST1. And as the plasma is very growing technology, so it is very much useful in the industrial purpose also, and then industry. Then a new institute was created in 1997 as the FCIPT, which is mostly using the plasma and developing the different technologies based on the plasma. Then after that, as we were already in the field of tokamak, so in 2005, India joined International Thermonuclear Experimental Reactor ITER program, and IPR is one of the countries into that. So 7 countries has joined, and IPR is also one of the countries into that. So this small introduction for this tokamak, what we are doing here. So this is a machine for the user, and the Russians first came with this idea, and they have given the name as a tokamak. Tokamak is nothing but the toroidal chamber with magnetic coils. So if you will see here that these are the different coils are here. In that, my this pointer is visible or not? I don't know.
Visible, sir. Your pointer is visible.
Okay, okay. So there were so many magnets. One was the central solenoid magnet was there, and these are the different magnets. So it's a one poloidal field magnet, and this is a toroidal field magnet. So if you will see this kind of device, this is fully of the magnetic device. So many kinds of magnets are there, and they are electromagnets, and it forms a magnetic case. Into that this plasma is held up. So this was the machine we have made, the first machine we have made, which is called Aditya. And you can, and a lot of technologies we are using. Yeah. Actually, this device was not for continuous operation, so we have to change it with the cryogenic superconductors. We have to use the cryogenics, then diagnostics we have to use, and then technology we have to use, then RF and microwave, then power engine we have to use, advanced material we are using, manufacturing techniques, new techniques we are using, then robotics we are using, we are using, and control data patient system. Yes. So if you will see this kind of documents if we are using, then we are aware of different technologies. So our field is not only from mechanical side, and we have to see each and every we have to knowledge. Otherwise, in research, we cannot progress further. So after this we have made the SST1. SST1 means steady state superconductor tokamak. So here we are having the magnets. So many magnets are there, which are superconducting. In superconducting magnets, we have to use the cryogenic fluids, different kind of cryogenic fluids. And so all the magnets which initially were from the copper magnets, and then we have tried to change into the superconducting magnets. So
Respected Gupta sir, your voice is not coming, I think.
now it is coming.
Now it's coming, sir. Okay, now it's okay.
Oh, okay. I don't know how this was muted. Okay, sorry. Hmm. So this was it, just aerial view of the picture for this ITER project. This is very big project is there where we are using, and we have made the cryostat here, cryogenic cryostat here, which was put here, and it was the biggest uh, vessel of the world, which was having the diameter of 29 meters. 29 meters, not the or something. This is 29 meter. By height was also 29 meters. And for this we have to make some cryo plants, and from there we have to flow the liquids to the. So this is already crash pad we have supplied. Cryo plant we are working over this here, and if I will show the one of the magnet. So this what tokamaks a lot of 200, more than 200 across the world. This you will see this which I was talking about the magnets. So this kind of magnets is the actual picture of the magnets. Here we are using the helium to make them superconducting inside the helium. But if we see that whenever there is helium, flow is there, and outside is the room temperature. If outside is the room temperature, then a lot of heat will come to this temperature. So because the radiation heat load will be very high, because 300 Kelvin to the 4 Kelvin, and radiation you all know that it is T to the power 4. So a lot of heat is coming to this, and we need a huge amount of helium to make them superconducting. Then what we have done, we have used the liquid nitrogen. Liquid nitrogen has been used as the outer case for this. So at each side of this magnets, we have put some liquid nitrogen panels. So whenever some outside radiation will come, it will go onto the liquid nitrogen panels, and from those panels only this heat load will come. So a tremendous amount of heat load was reduced into this. So these are the actual conducting coil which we are using at this time. These 16 parts are there, and whatever we are putting here, uh, we are just making them to slide, because whenever something is just cool down, then there will be some shrinkage and contraction will be there. So we are making them slide here on that. So this was just some brief introduction about our institute and where cryogenics we are using. So here we are using cryogenics liquid helium and liquid nitrogen. For liquid helium, we have the in-house plant. We are taking the gaseous helium, and then we are having some cold box, and then we are liquefying, and then we are supplying here. But for nitrogen, we are directly buying. We are not producing here. We don't have any plant because the plant cost was is a little high, and we are not industry. We will not supply outside for this. So it will be very cheap for us to just directly buy the liquid nitrogen and store it and then use it. So we have the capacity of around 1 lakh liter liquid nitrogen storage capacity. So for that we can supply it here. Now I am going just a brief introduction about what is the history of air separation. Why air separation is required? Because we are using the liquid nitrogen in our tokamak, as I have told in different this. So we need air to be separated and liquid nitrogen has to be generated. So if in 1985 you will see, then Carl von Linde performed an experiment, and in this experiment he made the liquefaction. He did the liquefaction, which was based on the air, and they have used the Joule Thomson effect, JT valve effect, and they have used the counter current heat exchanger. So it was one breakthrough in the cryogenic separation. So we will. This is our topic of the air separation by cryogenics. So they have used this cryogenic plant, but in the air separation history, plant history, a lot of work has been done after 1895. You will see different milestones are there. So in after only 7 years, the world's first area separation unit means ASU for the oxygen production was started. So this technology is not new technologies, but they are very old technologies are there. And 1904, this world's first air separation plant for recovery of nitrogen. Whatever nitrogen we are wasting into that in air separation, that was also recovered into that. Then 1910, world's first air separation plant using double column rectification process was developed. Initially, it was a single column plant. So we will see what is the difference between single column and double column. Then 1930, the development of Linde-Frankel process came. So first it was the single column, then double column, then after the Linde-Frankel process was developed. So 1950, the first Linde-Frankel oxygen plant without pressure recycling and stone filled reactors was produced. Then 1954, world's first air separation plant with air purification, because the air was not purified, so efficiency and other things, a lot of problems were there. So air purification by means of adsorbers was introduced, and then 1968 introduction of molecular sieve technology came for pre-purification of the air. In 1978, internal compression of the oxygen applied to tonnage air separation plant came. Then 81, the elevated pressure processes were introduced at that time. After the world's largest Barox air separation plant with variable oxygen flow adjustment was developed in the 1984. Then 88 first column, the structured packings came. So this is continuously development only here. If you will see this 20 years is gap there in 1930 50. Otherwise, continuously it is developing. In 1990, Linde introduced the argon production also, because argon is also coming out where we are separating the air. So oxygen and nitrogen is the main part, but this is also coming. And then world's largest air separation plant with packed column came in 1991, and in 1992 the ultra pure gases production was an ASU, air separation plant units. In 1990, after, so this is continuously you will see it is every year something new is coming, technology is coming. And worldwide, scaled radial absorbers and large air separation plant were used. Then 1997, the largest air separation plant built for nitrogen. So and with capacity of 10,000 TPD, fifth train added in train. We will see what is called train and how the things are moving. In 2000, development of advanced multi-stage bath type condenser is there. So here condenser used, we will see in my next slides. Then 2006, largest EPC contract was there for air separation in the history. was very big plant. Then 2008 reflux condenser was used for argon column, and 2010 advanced cryogenic process and efficiency optimized. After making so many effort, then efficiency is also optimization is required. In 2011 argon production without pure argon system was also developed. Then 2012 flexible high air pressure processes are developed, and 2015 simple filling of dual bed radial absorber. So absorbers are also playing a lot of role in this for purification. And then 2016 optimized fins for high pressure plate fin heat exchangers in the air separation units were there. And 2007 startup of world's largest air separation plant was there for the oxygen. So this is just a brief history for the air separation. If you will see, then 1895 to 2007 it is continuously growing, but main things remain same. Only the efficiency and new technologies are developing. So we are making different components according to those technologies. Why we are using cryogenics in air separation? So this is a small brief part for the cryogenics. The cryogenics is the IC cold. Cryo means icy cold and genix means production. So if we are producing the icy cold means very low temperature, then it is cryogenic. So different temperatures are there which we have achieved, and this is part of the refrigeration process. Above parts are there. And this line shows that below this temperature is divided and kept at 123 Kelvin. Below that we can see the liquid oxygen, liquid nitrogen, liquid helium, absolute zero. So these are called all the cryofluids. So if we are this making separation and then we are liquefying, then we are getting the cryofluids. Different cryofluids are there. And oxygen and nitrogen are the main components. So these are the cryofluids for us, which we are working. We are working on liquid helium and liquid nitrogen. Two we are working there. Now, what is the use of this inversion temperature? So this is a very important aspect in the cryogenics, that whenever we are liquefying of something, liquid nitrogen plants we are putting, a liquid oxygen plants are putting, whatever we are putting, we should know the inversion temperatures. And this is called GT, inversion temperatures. Why inversion temperatures are required? As we see, if we reduce the pressure, the temperature should reduce. But what is happening? Due to the high inversion temperatures or low inversion temperatures, we are saying that when if temperature is reducing, then we are this pressure is reducing, the temperature increasing. So if this is the case, then we have to use the pre-cooling before the JT expansion valve. So this is the and here if you will see, the helium has 43, hydrogen has 202, neon has 260. They are below the room temperatures. So whenever we are using this inversion temperatures, then we have to first pre-cool them up to this temperature. Below that, and then only we can use the JT expansion valve. Otherwise, we cannot directly cool them, because if we will reduce the pressure, then temperature will increase for them. So, but the air, nitrogen, oxygen, this we are can be cooled down and liquefied by GT expansion from room temperature. So directly, if we will reduce the pressure, the temperature will be reduced. So this thing by GT expansion. So this inversion temperature is very important. Whenever we are going to separate or we are liquefying to any cryogen, then we have to keep in mind this maximum inversion temperatures. And this is a useful range of the cryogenics, and this we have shown in two parts: below atmospheric pressure and above atmospheric pressure. So this is the line where at atmospheric pressure 1 atmosphere, and we are getting the liquid form. So this is the boiling points, or you can say these are the boiling points for that argon and this. So if you will see, nitrogen is there, which is having low boiling point. Then more than that is argon is there, which is having little higher boiling points than oxygen, that is also higher boiling points. This is around 77 Kelvin. This is around 88 Kelvin, 87 Kelvin almost, and this is 90 Kelvin. So like that, we are our concern is over this thing, but we can go to lower the temperature also. If we reduce the pressure, then we can generate some lower temperature also around 60 to 63. But we have to go sub-atmospheric pressure for that. And argon also, but liquid oxygen can go more than that, and this below that also by reducing the pressure. So our concern is nitrogen, argon, oxygen, mainly the nitrogen and uh, oxygen. So we are using this technology for the technology for different applications, and this is superconducting technology as we are using here this technology for our making the magnets, electromagnets as superconducting coils. So here we are using a liquid helium, and to reduce the heat load, we are using liquid nitrogen. It can be used for the gas separation and liquefaction. Yeah. And then this cryo is nowadays is almost using a lot of place using cryo preservations also, and in medical applications also we are using this cryo technology. So many experiments has been produced with the help of cryogenic technology, and we have to go for the air separation. So gas separation means air separation is part of that. Yeah. So we can different gas can be separated, and if we are using the cryo technology for the air, then it is the air separation for that. If we will see the air composition mainly, because we have to separate the air, so we should know the air composition. Air composition is mainly the nitrogen and oxygen. If by percentage by volume we will see, then this is 78% almost, then this is 20% by volume, and by weight this is 75 and this is 23% is there. Argon is also the next component is the argon, which is as 0.93, and remaining components are there in the rest of this. So if you will see here, this 78.08 and 20. This 95, then we will see that if you will take some volume of the sample, so air is made up of this around 99.03 of the total sample volume. So hardly 1%, less than 1% is there. In that also 0.93 is the argon. So argon is also there, but that is less than the 1%. And other components are there: xenon, neon, hydrogen, helium, krypton, and carbon dioxide. So these are other components, but these are very very less components. They are just negligible kind of thing components. So the above components where water is not present, so that's why it is called dry air components. So in air separation, we have to separate this N2 and O2 mainly, yeah. And these other things are maybe in the residual gases and can be taken as a byproduct, or we can take out argon also, because this lies in between this N2 and O2. The use of why we are separating out this nitrogen oxygen, because nitrogen oxygen both are very useful. We are using nitrogen in manufacturing industries. We are using nitrogen in the food and beverages. This when we are packing something, then dry nitrogen we are packing. Rubber and plastic industries we are using this nitrogen. Then healthcare also is used different thing in nitrogen, and research lab as we are using also the nitrogen. So then oxygen is also very important in the healthcare industries, and the glass and ceramic industry are also using oxygen, and the pulp and paper manufacturing is using, and then petrol refineries are using this oxygen, then chemical industry and A lot of examples are there, but I have shown only the few applications here. And as we have gone through this pandemic situation, at that time oxygen plants were required a lot. So the government wants a lot of oxygen units, plants, ASC units should be put so that oxygen can be supplied to the different medical uh, hospitals. So if you want to separate this air separation, then different technologies are there. So there are three main technologies which are existing for the air separation. This cryogenic process is there, one of the important process because it is a very old process nowadays. And then PSA came, this pressure swing adsorption technology came for air separation, membrane separation was there. So how these technologies are different? Because this is for different air separation is using different attributes with regard to different physical properties. It means some processes are used different properties of the nitrogen and oxygen and their different parameters. So these different properties and construct air gases, they makes the technologies different. So whatever attributes we have to use, that make the technology totally different with each other. So general properties which we can use for air separation are molecule sizes, difference in the diffusion rates through certain materials, the adsorption of the gases with metal, and the difference in boiling temperature. So these I have shown here four types like this. So these are the general properties by which if we are using something, then we can get different technologies like this. But this cryogenic technology has reached this mature stage. Means it is very long process and it is reached mature stage. While other technologies are in developing stage or semi-mature process. So they are also going to be matured or they are in some developing stage. But cryogenic is already reached to that stage. Now we have to see what attributes we are using, what properties we are using for critically for air separation. So this technology is based on the fact that different constituent gas of air have all different boiling points. As I have already mentioned that boiling points is the main property which we are using here to separate it out with the help of cryogenic technology. That's why it is cryogenic air separation. And all these gas, nitrogen, oxygen, and argon, they are at the cryogenic temperature. Boiling points are very low. So nitrogen is 77 Kelvin, and that is 87 around argon, and oxygen is 90 Kelvin. So argon is in between. So we are taking out this nitrogen on oxygen. Then in between argon can be taken out easily. So we are using the attributes or properties of the these boiling points. So manipulation of the environment, what we have to do for separation, we have to manipulate the environment in terms of temperature and pressure, how much temperature we have to keep, how much pressure we have to keep, and then air can be separated into the different components there. So basic process. Now I am telling the basic process which is applicable to all kinds of air separation uh, with cryogenics. So in cryogenics, there are five basic processes are there. Yeah. Yeah. One is the air compression, another one is air purification, and third one is the heat exchange, and then distillation and product compression and storage. So these are the five basic processes. If we can understand these five basic processes, then any kind of air separation plant you can understand easily. Because this everything is made up of this, but air compression, different kind of compressors can be used for that. Different kind of compressors can be used for that. So like that different technologies are there, and compressor things are different. And purification, we can use the different types of components into that also. So that's why this is the different condition for that. And heat exchanging, different kind of heat exchangers can be used for that. So this will make the technology different for that. And in heat exchange, this cooling of the incoming air, outgoing air, like this heat exchangers are there. Two-way heat exchanger, three-way, and distillation is also single column, double column. That it is also called a rectification column also. Then whatever product is our interest, that we can use it into that. So the property which we are using for air separation is mainly the boiling point. So boiling point has been both boiling points are little different for them, so we can use easily those boiling points technology. And molecular mass of nitrogen is 28.01 mole. This is colorless and odorless. So problem is with nitrogen and oxygen because they are both colorless and odorless. So we cannot differentiate easily by seeing the color or by having some odor here. This was the problem was there. But they are, so these attributes cannot be used for that. Molecular mass is different for them and boiling points are different. And this is the, one of the important that this is more volatile than the oxygen because it has the low boiling points. And this is less volatile, so we have to use the volatility of both the components for that. As I have told, some basic process. So these are the five process which I have told you into this. So air is compressed uh, into the air compression process here. And in this air compression process, we can use different type of compression. We can go to the different kind of pressures as per our requirements, as per our capacity of the plant and this thing. Then this air has been compressed and then it has to go for air purification. And in this air purification, we have to purify the air and we have to remove the certain components from that air. And the mostly in air we are having the water, carbon dioxide, hydrocarbons, and this thing. If suppose if if suppose we have not removed from here all those components means water, CO2, hydrocarbon, then it will prohibit says the vapor condensation will not be proper at that pressure. Then the liquid water solidification will be there, and gases CO2 will also conditions will occur. So all those problems has to be solved here. So air has to purify. So mostly only this other components which are not required can be purified here in the air. Then this air has been fed to the heat exchanger, and in heat exchanger, we are using the we are removing the heat of the incoming gas, uh, incoming air, so that the efficiency of the product or this can be increased. So from heat exchanger, you are seeing here the heat exchanger. Uh, one is going to the distillation. This is the heart of the whole process. This is the main part of the distillation. So we will see in detail because this is the main part of this. From distillation, we are getting two different components. Two different components we are getting in nitrogen and oxygen air. We are separated into those two components, and these two components can be fed once again to the heat exchanger because the temperature here is low and here temperature is the high. So we can use this low temperature to cool down the uh, okay. So
अभी मेरा बिल हो गया है 450 का ना, 350 का,
yes,
350 का वो सैंडल और ये 100 का ये, और एक वो ट्राउजर भी।
some
हाँ वो अब आपने वो व्हाट्सएप में लिखा ही हुआ है सब, बस तो उसमें से देख लेंगे। हाँ बस
Jani sir, can you mute them?
बीच में 442 दिखा रहा है एक बार। 442 आपके साइड में 442, मेरे में 449।
Hello.
अच्छा था, मैं रुक गया, मैं बोला चल 280 भी हो गए थे, 300 का 280 तक आया था। ओ बाप रे, मैं बोला चल बुक करता हूँ, घर जाके करूंगा यहाँ की वजह।
Hello, Jani sir.
तुरंत कर ही देने का है तो यार।
Hello. Hello. Hello, Jani sir. Hello. Hello.
हाँ yes sir, sir you can continue sir. Yes sir, your voice is coming sir. Yes sir.
But so many voices came.
Yes actually by mistake वो mic sir ये हो गया था सर। आप
हाँ
कंटिन्यू
हाँ.
कर सकते हैं सर। थैंक यू
Okay.
सर, सॉरी सर। यस
Okay.
सर।
Thank you. So then, if we will see this distillation, then we can we can go in detail into distillation part. But heat exchanger, whatever the high temperature air was coming due to air compression and other things, that can be cooled down here. We can use the cold part or low temperature heat part to that, so that the heat exchanger will be there. And whatever product we want, either it is nitrogen or oxygen, so those products can be go to the product compression, where we can compress the product which is of interest, and remaining can be come as a byproduct to this. So this is five basic process are there. In any kind of air separation plant will be there. Then different these only five process are the main process. Remaining other things are not there. Other are only just to control all this process. This. So this is the main heart of this. So overall five process, distillation process is the heart of overall process. If it is because this is only used for the air separation, distillation is used for the air separation, and this is used for air into its constituent means nitrogen and oxygens. So whatever output is coming from distillation process, they are fed back through the heat exchanger in order to realize cold recovery. Because outside, when distillation outside is coming, this is a cold product, and from here it is going hot, so heat is exchanged into that. So cold recovery, we can take, we can use the energy of cold energy, so that is needed for the cooling of the incoming air feed lines, this thing. And the main air product is at low pressure when exiting the distillation process. As I told that whenever it is coming from the heat exchanger, this thing. So this is at the low pressure. But we need the high pressure as per the customer requirement. So then it is usually compressed to client pressure, whatever he is required at that pressure and prior to delivery. And this distillation process, if we will see, then it has the three general components. First, we have to see air separation process has five basic process. Out of five process, distillation process is the important process where we are separating. Into distillation column, there are three main parts are there, general components are there. One is vaporizer, many are calling as a boiler also, then condenser, and then the trace sets. Trace sets I will show you into that. So this I am showing the distillation column. This is just a schematic of that. This is not actual. This is a schematic of that. So into this the distillation column, we are feeding the liquid, we are feeding the mixture of nitrogen and air, and then we will see that the vaporizing. We are having this boiler below, and it is vaporizing the gas, and this gas is going up, and this condenser is there. As I told, three component: vaporizer, condenser, and they are the tray sets. Different tray sets are there here. Yeah. So vaporizer is producing the vapors of that component, both mixture, and then that mixture is going up, and from top side we are condensing them. Then whatever condensate is coming, this is coming in the form of liquid, and this liquid is coming to down. Again, this is in the means contact with the paper. Then again it is coming down. Then again it is coming. So like that, different kind of this trace sets will be there. But mostly thing are there that most volatile component will go upside, and less volatile component will go here, will be stored here. So this will separate it out. Means two components are there. So as I have told in previous my slides that property, nitrogen is more volatile. So nitrogen will go upside and oxygen will come downside. So this is the attributes of property which we are using as per the boiling point. So the distillation is made possible by efficient liquid gas contact. Whenever there's this is a liquid is coming and gas is going. So here always the liquid gas contact is there. Yeah. So proper contact between descending liquid and rising gas. So gas is rising up, and this liquid is coming. So there should be proper contact. That's why design of these trays is very important. So it is separate, complete separate part. They have to design these things. Okay. So the respective purity of the most volatile and less volatile elements differ at each tray. Means from here some purity will be there, then again it will be this upper part will be more pure, and the liquid is coming down, that is also purity. Each tray purity is changing. That's why different trays are there, because it is enriching in the, if it is going upward side, then it is enriching in the most volatile component, means nitrogen is mostly present. When it is coming down, then oxygen is more present. So at each tray this purity is changing, and we can get the higher most pure at low side and most pure at upper side here. So with lower and upper sides of the distillation column being the two extreme, which is also where the pure elements are obtained. Here mostly we are getting nitrogen, but is most volatile, and here we will get the oxygen. So this will separate it out. Air is separating out here in this. Yeah. So if three sets are there, then we are using the property of cooling and partial condensation of the rising gas. When vapor is going, it is come in contact with the liquid, then it is condensate. But this is partial condensate, and then it will go up once again. So both property we are using, heating and partial vaporization of the descending liquid. Whatever liquid is coming here, when the high temperature vapor will go, then it will heat the liquid, and the vapor, it will convert the vapor. Same time, whatever the gas is there, it will condense. So this is the cooling and heating process at the tray level. So each tray level, heating will be there and cooling will be there, but we are using partial condensation of this and partial, so that the heat can be balanced here. And the tray provides the rising gas with a certain resistance, and thus creating a pressure drop. Actually, these plates are not simple plates. If gas is passing through this, then it is perforated plates. So there are so many holes are there in these plates. This I will show you there. So if we will go, if we will see, then pressure drop will always be there in between these cooling channels. So this pressure drop must be as much as possible. Otherwise, this flow will not be there. This gas will not pass if pressure drop is high. So otherwise, we have to create a higher pressure here, and then it will go. If too much high pressure is there, then this liquid or gas contact will not be proper in this, and a significant energy consumption will be there. So pressurize this thing and air compressor will be used. So we have to see, we have to design this air tray in a proper manner, otherwise we are not able to get proper things. So we are using this whenever we are designing, we are using temperature composition curve using. So oxygen and nitrogen here, oxygen less volatile would be produced at the bottom, as I told. Oxygen will come here, nitrogen will go up. So if you will see one bubble of the gas, nitrogen air vapor is there. This we are showing at some in tray condition. So liquid is upside and this gas is there. So some bubble kind of thing will be generated here, and whatever vapor is coming, that will be condensed. So this O2 will be condensed, and this liquid will be evaporated here. So like this is a process happening at the tray side. So as vapor wall moves up, it becomes richer in low boiling point component, that is N2. N2 is increasing as it is going outside, and O2 is coming down, and N2 is going up. So as the liquid moves down, it gets richer and richer in the high boiling point O2. That's why O2 is produced here, and this N2 is produced upside here. As I told you that these are the columns. These are the actual columns are there. So in this, these are the trays, and these trays has to be designed properly. A lot of holes are there. You will see these are the different positions where uh, these are the components, and in between so many trays are there from here. So these are very perforated holes in each tray, and these trays are designed. These trays are designed based on the temperature composition curve, and with the help of enthalpy composition curve. Enthalpy composition means mole fraction versus enthalpy. If I am telling composition means this is mole fraction of that. So if nitrogen and oxygen we will see, then the curves are almost horizontal for vapor, and like almost, this is not perfectly, but this enthalpy composition curve is almost this. So we are using the two things here: temperature composition curve and enthalpy curve. Then only we can design this kind of plates. And in this rectification column, these are called distillation column, rectification column. Upper side can be made as a, suppose here this can be made as a dome, this can be made as a dome. That depends upon different kind of how much surface we need, how much things we need. So according to that, and in this also so many bubble caps are also capped, bubble caps. So each having the cap, each having the cap, this thing, but this is comes under the design. And if we are designing, then we have to use the principle of Murphy efficiency. So I am not going into that detail, but Murphy efficiency is also one of the important part for designing the tray. And this Murphy efficiency is providing this whatever a column is there, then how much vapor and liquid is uh, interacting with each other. Yeah. So if it is good, then Murphy efficiency will be very high, and this Murphy efficiency is on the depends upon the size of the bubble, how much time of contact here is there, and what are the overall mass and heat transfer coefficients are there. Next, so different kind of air separation systems are there. based on this distillation column, and this depends upon quality of product which this kind of system we are using, and recovery of products, what recovery we want to make, and then effectiveness of the system. So these different kind of system can be designed easily. Yeah. So there are few systems which we have shown here. Linde single column system, as I told that starting this Linde has done experiment for liquefaction. It was used the single column. This was not separation, but starting of their separation, they have used single column system. Then they have used to double column. Then they went to Linde Fenkler. This Hilland system is there. Then Linde Brown system. Then air liquid system is there. So different kind of systems are there as per different configuration. But the basic process, basic design of the distillation column or rectification column will be the same. Will be same. So I am going the very basic system which we can use it uh, for understanding the philosophy. So this is most simple air system in a single column system. So it was first operated in Ireland in 1902, as I told in history that after 1895 the liquefaction was done. Then they have made use for the air separation 1902 after around 7 years after that. So here is the compressor. I told five process I have told you. So this was the first process. Air compress. Air is there and it has been compressed here. Then it has to be removed. The purified air purification is there, where we have water, carbon dioxide, and hydrocarbons are removed from here. Then this air, purified air, has been given to the heat exchanger. This is the heat exchanger. This is symbol of the heat exchanger. Then this air will go to the distillation column here, and as it is hot, this is hot, so it will work as a the boiler vaporizer here, because whatever here liquid is present, and it will boil it here, and then it will go upside, and this air is then expansion. This is the JT valve is there, expansion valve. So when we will expand it suddenly, then it will convert into the liquid part, and this liquid will come here, and this will go down through the different trace sites here. And above part, whatever this nitrogen has been produced at top side, then this nitrogen, this is cold nitrogen. This is not very hot nitrogen. This is cold nitrogen. Then this cold nitrogen is passed through the heat exchanger. So this heat exchanger will be, this is cold and this is hot. So heat exchange will be there, and this will make them cold again. So this cold air will come here, then again it will go. So by this process easily, we can use the complete efficiency for the heat exchanger. This is two. I have shown there three, so there are three process heat exchangers also. Suppose this is three process system. So whenever air is there, it is just compressed here, then again removal, and this here the change is that uh, we can use two stream heat exchanger or three stream heat exchanger. It will increase the efficiency of that, but we have to design in a proper manner that how much cold things we have to extract and given to the heat exchanger. So from here this air will go, and this will come down here. It will be used as a boiler or vaporizer, and then it will expand, and then it will go from down, and these are the different kind of trays are there. So this nitrogen is there, so this is same as previous this one. But what we have done here, whatever here liquid oxygen was there here, so we have taken out a small part of liquid oxygen which was coming out here. We have taken out, and then we have supplied it into the heat exchanger. It will give two purpose. We can uh, make this liquid oxygen into the vapor or gaseous oxygen, purified gaseous oxygen, because here the most pure oxygen has been contained here. So we can get here the most purified oxygen, and then it is vaporized. So we have used, because this is a hot and this is the two system. This will make cold and this will become hot, because heat exchanger will take from incoming air which is hot to the outgoing cold. So it has very nice combination that it will reduce the temperature of air which is required at here. And similarly we want to make the purified gas oxygen, then it will make the convert into the oxygen liquid to vaporize. So we are using the energy easily here, exchanging energy with the heat exchanger. And this is the double column system. Yeah. In this column everything will be the same, only the one column upper side and below column, two columns we have made one above the other. Yeah. So in this we are producing the LOX product here and LN2 product here. Whatever enriched liquid air is there, it is given here. It will come down. Liquid nitrogen will here. We will collect the liquid nitrogen here and LOX here, liquid oxygen. So this is double column, one column over the other column, and this part is combined. Combined means this is condenser. Each column has one, upper side is condenser, lower side is boiler or vaporizer, and here the boiler part was mixed with the condenser. So this is the condenser reheat boiler part is there. This I am showing the generic air separation unit. So air separation unit, generic air separation unit is there. In this the same thing, that air is feed here. This is a PID diagram. It's not, instrumentation is not there. This is just a line diagram. Air feed is there. Then it is filtered here. By filtering the different kind of sand particle and this particle, other particles has to be filtered here. Then this will go to the compressor. After compressor, there are the liquid oxygen. We have this water. We have to separate it out here, and remaining other gases with the mold sheets we can take out here. So liquid here we are taking out water, and then here gases, which is CO2 and hydrocarbons. So impurities are, this is the impurity part. This is air the compression part. 5 basic process. First is compression is taken place. Here the purification has been taken. Impurity we have taken. Then from here we have to give this thing into the heat exchanger. Heat exchanger. It will be cooled down here, because the whatever other things streams are there, they are at low temperature, so they will warm up. They will warm up, and this is hot, so this will be cooled down, and this will go to the same. This is heat exchanger, then this will go to the column here. So this is partially condensed there, because it has lost the heat from here. So this is partially condensed there, and it will go to the cryogenic distillation here. And in this distillation, we are having the three parts. Three, because LOX having the 90 Kelvin will be at the down here, because this is less volatile, and argon is in between, so we can take out argon also in between, and then liquid nitrogen, which is most volatile. It will be at the high temperature. So liquid nitrogen will go here, and if we want, then we can go directly for compression. So this is one part, another process, then heat exchanger, then distillation, and then the product compression with that. So truck loading with the customer. So you can directly go to liquid nitrogen, and it will come out. Liquid oxygen and this. And whatever organ is coming, if it is liquid form we need, we can take out. Otherwise, if we want to gases, then it has to go to the vaporizer part. Vaporizer liquid organ has been vaporized, and then this argon will go to the gaseous argon, and here we can compress the air as per the user conditions. Similarly, liquid nitrogen we are taking out, and top part, this liquid nitrogen, this gaseous nitrogen is coming out. This we are making warm, and then we can taking out this gaseous nitrogen here. Some part we can bleed it out, and internal refrigeration we can use for internal refrigeration to the cold box. This thing here, and liquid oxygen we are taking out here, and small part of oxygen has been taken out from here for purified if we want gas oxygen. So as medical and other things, a purified gas oxygen is required, then we can take out from here, and we can pass through the heat exchanger. So by heat exchanger, gaseous oxygen we can produce. So if we will see this air separation unit, we will see then we have already got three part here: nitrogen, liquid oxygen, and liquid argon. Similarly, you can get from air separation unit gaseous argon, gaseous nitrogen, gaseous oxygen. So this is comprising of the all the components in the liquid form and the gas form, and water and other thing has been taken out. So this shows the internal relationship of major component. Especially plants will vary. Plants will vary in the heat exchanger types will vary. The column number of trays will vary. Type of trays will vary, and hole size will vary like this. And sometimes we when the fed stream if suppose enters into two-phase flow, two-phase liquid, then flash calculation is also required. We have to use the flash calculation into that condition there. And for this, if you want to, this columns are there. There are two types of plates are there here. As I told, trays are there and plates are there. So in that you can use basic method of Ponson and separate, and Macway and Thele method you can use for them. So because it is two types are all already there into this plate type, and packing type is there. So different packings we can put into that. And whenever we are designing the number of theoretical plates, whenever we are designing the plates or trays, number of trays, we can keep more than that, because in actual condition the number of plates will be more, and this is the only less theoretically is coming less. So this can be of mostly this is of two type of this column is of two types. Mostly packed column. Packed column is they are cylinder filled with a packing material with metallic rings and wire gauges are there. Packing material provides large packing. If we will pack it at different place we are packed, then it will provide a large surface area, but this is not so frequently used in cryogenics system. We are using the plate column. So in plate column, small holes are there, and fine mesh and then bubble caps are there. So like that, you can use it. Then for if you want to go for oxygen plants, then air needs to be compressed. For if you want only gases oxygen, not the liquid oxygen, then the air compressor can be from 30 atmosphere to 60 is enough. But if you want to liquefy also, then we have to go for the 200 atmosphere for effective. But in column, it is hardly 1.3 to 2 atmosphere in air column. So whatever is coming out product that is at the low atmospheric pressure, then we have to give at the higher. So then again we have to compress it. So if we will see the key industries into this, then key industries are Linde is there, which is supplying this air separation ASU plants. Then Air Liquid is also there. Then Praxier is there. This is also one of the good company, Air Liquid and this. And mostly we are using all those companies, and Air products and chemicals are there. Then Thiomethane Sensor Corporation is there. Then Messer Group is there. Then this Universal Industries, Energy Flux is there, and then Technax is there. Gandhinagar. So many companies are there nowadays in ESC because this is mature technology nowadays. Only we have to put the plants into that. So if we want to conclude, then to increase the capacity of the plant, number of trains can be added. Number of trains means the number of small units. If we can add together, then the total capacity of the plant can be increased. As I have shown in that train means one unit which is producing the liquid nitrogen. So if we are adding the one by one, then capacity of the plant is increasing, and the capacity is measured in terms of TPD, means tons per day, how much tons per day we have to use. And if we want to use 50 TPD, suppose capacity is 50 TPD for that, then the cost is approximately 2 crores for that. And the flow of air products is usually quantified in terms of normal meter cube per hour. So we have to use the how much flow we want, how much that is already measured in this Newton meter cube normal. So normal cubic meter per hour, and normal cubic meter per hour means at 1 atmosphere and the 0 degree centigrade, whatever flow is there. So we can calculate according to that. The cryogenic ASU are in mature stage and the production can be enhanced as per the requirements. So now different technologies are coming to make these systems only highly energy efficient. But in cryogenics, so many technologies are already developed for energy efficient, and various key industries are ready to supply the plants in the India. Thank you very much. Any question?
I participants to put any question, doubt, difficulty to Gupta sir as he presented air separation technology in detail, as well as give a very quick introduction about ITER project. Okay. Inviting participants to put any question to the sir, or either having difficulty in speaking can write to the chat box also, so that we can read and ask from your behalf to the sir. Thank you, sir.
Okay, thank you. If suppose no questions are not there, if they want to ask later on, then they can write to you and you can forward it to me, then I will give the reply to all the questions.
Yes, okay. Now, as there is no question from the participant,
Okay.
we can end the today's session here. As I think Dr. Sasar in the meeting, I requested Dr. Sasar to give the vote of thanks to the Manoj Kumar Gupta sir.
Yes, sir. Thank you very much, Gupta sir. At very short notice, we had informed you to give your expert session on use of cryogenic technology for air separation, and I have seen you have very nicely given all the details, all different types of air separation plants. In fact, our first session was by one executive from Linde, and in continuation with the on same line, this topic was delivered. And considering air separation technology, which is highly important these days as more and more oxygen plants are being installed, being mechanical engineer, in fact, in most of the curricula of different universities, though refrigeration and air conditioning is maybe one of the subject which all students have to study, but this air separation technology is limited to students either of referee AC group or students having cryogenic as their elective group. So in general, all faculty members must be knowing this technology. In fact, in our Gujarat state, Gujarat Technology University had given duty to faculty members to assess this cost of oxygen installation plant and their performance to faculty members of different universities, different institutes affiliated to GTU, and so many faculty members in fact were not knowing full detail working of oxygen plant. So I thought that this technology, whatever developments there are, must be known to all faculty members. And considering cryogenic plant there is at Institute for Plasma Research, I remembered you, and at very short notice you could deliver this topic very nicely. Thank you very much, sir, for accepting our invitation and delivering this nice talk. Thank you very much, sir.
Thank you very much, sir, to give me the opportunity to just share some experience. Thank you, Dr. Jani. Also.
Thank you, sir. Thank you. Now there are some instructions for the participant, as we have provided the feedback link in the chat box for the session of Manoj Kumar Gupta sir regarding air separation. So provide your valuable feedback, and whatever may be the session going on currently Monday, Tuesday, Wednesday, and the PPTs of the concerned faculties available to us with the kind request that can be shared the WhatsApp group, as well as some of the PPTs also provided on the portal. So you may use and study this PPT for your reference, because we have to conduct 150 marks, 50 question test on the Friday. So it is based on the questions to be provided by the expert based on the expert session completed among these expert sessions. So you may have to attend all the sessions carefully. Whatever may be the questions to be asked in the FDP test on Friday will cover the syllabus, or either you can say the topics to be covered under the expert session. And as ATAL portal having one limitations that they have recorded your attendance continuously, and your 80% attendance will be required. If your attendance is not there, anyhow you score in the test will not made you to get your certificate, and minimum 60% marks to be secured in the test also is mandated by the portal, because it is automatic portal. We cannot do anything from our side once your result will be poor. So I request all the participants to be seriously attend the test available online time in the meeting, and to get through what are the sessions to be covered. Rest available PPT with the consent of speaker we will also get shared among you. So thank you. Any suggestions, any query from the participant, any difficulties to be found? Most of time you are requested to log in the ID. With that login, you can refer our recorded, post-recorded sessions available in our team meeting, so that if some of the portion may get missed due to voice or some internet connectivity, can be later on be referred continuously as a session lecture of 2 hours by you in the future. That is for education purpose. Don't do share these lectures among anyone on the large scale. I invited participant to have any suggestion, any difficulty that might be faced by them, or whatever may be the any kind of suggestion, some improvement from our side, so that taken care. our next session will be most probably started in time, and sir will be available as per the message is conveyed to us. Next expert speaker is